Hello, I'm here to do part 2 of a projectile motion problem. Part 1 was we had a softball thrown from the pitcher's mound and we were throwing it horizontally at that point. This time I'm going to throw it at a small angle upward and we're going to see how that changes our numbers. So just to review what the problem was, you're throwing out the first pitch at a Blue Devil softball game. You're on the pitcher's mound, which is 0.28 meters high. You throw the ball at a small angle. The ball leaves your hand at 35 meters per second at an angle of 7 degrees above horizontal. We want to know how fast it's going and how far does it fall by the time the ball reaches home plate. So it's the same questions as before, but now instead of throwing it horizontally at 35 meters per second, we're going to throw it at just a little bit up. So we're going to do the same thing as before. Start with our picture. So there's our pitcher's mound, here's us, and we're throwing the ball, but this time we're throwing it upwards at 35 meters per second. Still 12 meters, 12 meters? Yeah, 12 meters to home base. And the mound was 0.28 meters high, and we throw the ball, and it leaves our hand 0.85 meters, above the mound. So we want to know how fast is it going when it reaches home plate and how far has it fallen. Same two questions as before. Alright, so you might say, well, how is this any different? And it is. It's a very subtle difference. Let's do our two directions again. Oh, we got to get our origin. Let's call that 0, 0 right there. And our standard up is plus, to the right is plus. So I'm going to do my horizontal components, x initial, x final, v initial, v final, a, t. Let's put x's on all of those, because those are all just the horizontal piece. And then we have to do the y's separately, because these two are independent of each other. Y final, v initial, v final, a, t, y, y, y. All right, so we've got our horizontal information, we've got our vertical information. What do we know horizontally? I set my origin horizontally to be right where the ball starts. And we want to know information about it when it reaches 12 meters away. Initial velocity horizontally. Now that 35, last problem, we were throwing at 35 meters per second purely horizontally. So all of our initial velocity was horizontal. Now we're at an angle. So this isn't 35. This isn't 35. Neither one of them is. So let's skip that for a moment and let's see what else we can do. We know for anything in projectile motion, there's no acceleration horizontally. Vertically, we know the acceleration is the acceleration due to gravity. Y initial, that was 1.13, I think, when we added up those two. Yep, 1.13 meters. This was a question mark. We want to know how far it's fallen when it gets to home plate. And we wanted to know how fast it's going, so we need to know that and that. We don't know anything about time. Alright, so why is this different than the other one? Because of that small angle. If we have the ball going up at an angle where 35 meters per second is our initial velocity, and we're at a 7-degree angle, so we're going upwards just a little bit. What we need to do is figure out what our initial velocity x component is. So what part of this is just the left-right piece, and what part of it is the up-down piece. So this is going back to vectors and our trigonometry. The x direction, that's adjacent to my angle, my 7-degree angle. Adjacent is the cosine component. So adjacent gives us the cosine component. So VI times the cosine of theta. VIX is 35 times the cosine of 7 degrees. All right, what do we get if we do that? It's not a very big angle. It should be close to 35. Yep, 34.7. All right, so VIX is 34.7 meters per second. VIY, it's opposite the angle. That's our sine component. So 35 times sine of 7. And that's going to be a small number because 7 degrees is tiny. I do the math, I get 4.27 meters per second. So what these represent Out of that 35 meters per second going up like this, 34.7 meters per second are left-right, and only 4.27 are up-down. This is what goes into our chart. So this is what we bring in here. So VIX is 34.7. 34.7 meters per second. All right. VIY was 4.27, and that was going up. So yeah, positive. And this is going to the right, so that's positive. And as we had last time, since it's projectile motion, there's no horizontal acceleration, which means we already know this. We know that our final and our initial velocities are exactly the same. Plus 34.7 meters per second. Got it. Same two questions as last time. How far has it fallen? And what's our final velocity? So I'm going to do exactly the same equations. We just this time have not 0 here. Which is going to probably mean it's a quadratic. Yeah, it might. Okay. All right, so last time we needed to figure out the time from our x. So I'm going to start with that. We did the long equation to get time. So I think we can still do that this round as well. 1/2 at squared x, 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 x. Anything 0? My initial position is 0, and my acceleration is 0. So x final is equal to v initial x times time, same as what we had last time. X final over v initial x. So this should be just very slightly different than last time. Last time it was 35 here, now it's 34.7. So my guess is, let's see, we're dividing by a slightly smaller number. Our answer should be a little bit bigger than before. 12 meters over 34.7. So what do we get with that? This time we have 0.346 seconds. Last one was 0.343 seconds. Okay, not very big difference because it's this tiny little angle. We know our time now. Now we have time, we can get this one and this one. The easier one is our y final. Y final equals y initial plus v initial t plus 1/2 at squared, all in the y direction. Anything 0? Oh, look at that. No zeros this time. Bummer. So, quadratic. We've got a time squared. Oh, it's not a quadratic. We're not solving for time. We're solving for y final. We know that, we know that. We now know time. We know that, we know that. Not a quadratic. Yay! Y initial, 1.13, plus v initial y, 4.27, times our time, 0.346, plus 1/2 times acceleration, negative 9.8, time squared, 0.346 squared. So, it's pretty straightforward actually. If we do that, we end up with a y final value of, really, I end up with a y final value of 2.02 meters. What the heck is going on there? Last time, when we fired it horizontally, launched it horizontally, it dropped by 0.58 meters. It dropped by over 1/2 meter. What's going on if we end up higher? Does this make sense? Again, every time you come up with a number, does it make sense? So we were launching it upwards very slightly. So instead of, I don't have room, instead of going and falling, this time we were launching it upwards. And I'm not sure if it was moving up or down at that point, but yeah, it ended up rising. Huh, okay, so it didn't fall, it rose. And it rose, how much? 1.3 to 2.02. 0.8 meters. Okay, so the answer here, rose by 0.89 meters. All right, well, I guess that's that. Now the other question is, what's our final velocity? We're going to do the same thing as we did before. We need to find out what our v final x is and our v final y. I need space. So, what is our v final y? So while I'm erasing, you can go look for an equation that will get us v final y. I can think of 2 of them that would work. And, well, I think they'd work. We know time. We know everything but v final y. Yep, we got 2 equations that have v final. They're both going to get you the answer. So, pick your favorite one. Do you like the squared one or not? V final equals v initial plus at. Why? Oops, I'm in the wrong color. Bad me. Bad me. We don't want that. Okay, orange color. Got to keep them straight. Now I just did the wrong thing there. Try again. 3rd time's the charm, right? V final y equals v initial y plus a y t. V final y is what we want. Okay, equals v initial y, 4.27 plus a, negative 9.8, times our time, which was 0.346. V final y, when we do that, is, what do we get? What do we get? Oh my goodness, 0.879 meters per second. Now keep in mind, this is a velocity, a final velocity. So, at 12 meters down the road, when the ball is right over home plate, it is actually still moving up, but it's really close to its peak. So it started at 4.27 meters per second, and it's gone up and it's slowed. We're right there. Okay, so we have our v final y. We can put that here, 0.879 meters per second. And then we just have one last step. We need to figure out what that triangle is, that final velocity triangle. And if you just watched the other video, you should know what to do. So, if you just watched the first part of this video, go ahead and pause and see if you can figure out what your v final is going to be based on what you learned from the last one. So what do we have? We need to put together these 2 into a triangle. Alright, so I've got v final x, so to the right I'm moving 34.7 meters per second, and then up down I'm moving, okay, this is going to be a ludicrous looking triangle. Up down I'm at 0.879 meters per second. I'm going to move that one to the right side. Okay, so I can tell you that this is going to be really close to 34.7 for that vector because, again, if you think about this on a scale, 34.7. So 34.7, that's like centimeters would be this, and then less than 1 centimeter. It's going to be tiny. All right, so our final answer is that thing right there. Our final velocity is this vector right here at this angle. And to get that, we're going to do the Pythagorean theorem. A squared plus b squared equals c squared. And with that, I get 34.7. Yeah, I knew that one was coming out that way. 34.7 meters per second at an angle of, a whole 1.5 degrees above horizontal. This is a tiny little triangle, smaller than our 7 degrees that we had. Okay, so last one with the horizontal pitch. V final was 35.2 meters per second at 5.5 degrees below horizontal as we were going down. Here, with a 7 degree upwards pitch, we are at 34.7 meters per second. That's our total speed at home plate, as it's over home plate, at theta, the angle, 1.5 degrees above horizontal. We're still going up very slightly, so if I were to do this, I would have to cut it off like there, where we're still going up. Not much. So did we answer the questions? The questions were, how fast is it going? 34.7 meters per second, going up at 1.5 degrees above the horizon, horizontal. And how far has it fallen? Well, it hasn't fallen. It actually rose by about 90 centimeters, 89 centimeters. Reasonable answers, even though some of them were kind of weird, rising that. But it does seem reasonable. It makes sense compared to our other problem. So I think we've got this one done. All right, good job.